Welcome to this episode, where we're diving into the intriguing realm of distributed systems, with a particular focus on causal consistency. As technology continues to evolve, the demand for systems that can effectively manage distributed data while ensuring reliable operations is becoming increasingly critical. Today, we'll explore two notable projects in this area: clusters of order-preserving servers, or COPS for short, and Eiger. We'll look into how these systems tackle the challenge of consistency, the techniques they use, and the trade-offs they navigate to maintain both reliability and performance. So what exactly is causal consistency? It's a model that helps distributed systems maintain a coherent view of operations, even when messages arrive out of order. This is especially important for applications that rely on a dependable sequence of events. Both COPS and Eiger approach this challenge in unique ways. COPS utilizes key versions to keep track of dependencies, while Eiger aims to establish a clear order of operations. One of the standout features of causal consistency is its ability to reconstruct event sequences. By employing techniques like vector clocks, these systems can maintain a partial order of events. This capability is crucial for resolving conflicts, as it allows systems to manage discrepancies that occur when operations are executed out of sequence. Various consistency models, such as read-own-writes and monotonic reads, ensure that clients can reliably observe their actions, which ultimately enhances the user experience and builds trust in the system. As we continue, let's shine a light on session models, which provide a client-centric view of consistency. These models focus on the individual client's interaction with the system, ensuring that their experience remains consistent and reliable. By emphasizing how clients perceive and engage with data, session models effectively bridge the gap between technical implementation and user experience. This client-centric approach is particularly relevant in distributed systems, where the complexity of operations can sometimes lead to confusion or inconsistency from the user's point of view. By implementing session models, systems can create a more intuitive experience, allowing users to interact with data in a way that feels seamless and coherent. Now, as we delve deeper into the mechanics of distributed systems, we encounter the crucial trade-offs between availability and consistency, especially in eventually consistent systems. In these scenarios, updates propagate asynchronously, which can result in different nodes having varying views of the data. This is where conflict resolution strategies become essential, as they help determine how to reconcile discrepancies that arise from these asynchronous updates. A key concept in this discussion is quorum. Essentially, a quorum means that more than half of the nodes in a system need to agree on a particular operation. This mechanism allows systems to keep functioning even when some nodes fail. However, it introduces its own set of challenges. If too many nodes are down, achieving the necessary consistency can become impossible, leading to potential issues with read and write accuracy. To tackle the challenges of maintaining consistency, we can explore techniques like blocking read repair. This method ensures that when a read operation is performed, the system checks for the most recent data and repairs any inconsistencies before returning the result. While this boosts the reliability of reads, it does come with a trade-off in terms of system availability. Striking the right balance between ensuring consistent reads and maintaining system uptime is a crucial consideration for developers and system architects. Another important aspect we'll discuss is tunable consistency, which gives developers the flexibility to configure the level of consistency their applications require. By adjusting quorum requirements and other parameters, systems can find a balance between the need for consistency and overall performance and reliability. This flexibility is especially valuable in environments where different applications have varying needs for data consistency. The implications of these configurations are significant. For instance, A system that prioritizes consistency might experience higher latency as operations need to wait for a quorum to be reached. On the other hand, a system that emphasizes availability might risk serving stale data. Understanding these trade-offs is essential for designing effective distributed systems that cater to the specific needs of users and applications. Latency, too, plays a critical role in our discussion of distributed systems. As we navigate the balance between consistency and availability, we must also consider how latency impacts user experience. High latency can result in delays in data retrieval and processing, which can be particularly detrimental in real-time applications. Therefore, optimizing for low latency while still maintaining an acceptable level of consistency presents a key challenge for system designers. In wrapping up our exploration of causal consistency in distributed systems, we've highlighted the intricate balance between consistency, availability, and performance. Through the lenses of COPS and Eiger, we've seen how different methodologies can effectively manage dependencies and ensure reliable operations. The significance of session models and client-centric approaches further underscores the need to prioritize user experience in system design. As technology continues to advance, grasping these concepts will be vital for developers and engineers working with distributed systems. By navigating the trade-offs between availability, consistency, and latency, we can create systems that not only function effectively, but also provide a seamless experience for users. Thank you for joining us in this insightful discussion, and we look forward to exploring more topics in the world of distributed systems in future episodes.